All right, we're going to get started on 2.4. And the first thing I want you to think about is what does it mean for function f to have a limit, essentially, as x approaches some value c? What exactly does that mean? Because so far, the limits that we have been working on, they are called two-sided limits. And what I mean by that is we were looking at a limit as it approached from both sides to a single point, from the left and from the right. So we had some curve or something, and say we were looking at what's the limit as it approaches that point. We looked at, hey, what was happening as we approached from the left, from the positive side, and as we approached from the right, from the negative side. I'm sorry, I said those backwards. As we approach from the left, the negative side, and from the right, the positive side, like that. And we saw what was going on there, and that's basically the limits we've done. But take a look at this one here. If we look at this function here, we're going to get different values depending on which way we come from. If we come from the right, if we come from the right from the positive side, it's going to approach a value of 1. But if we come from the left from the negative side, it's going to approach a value of -1. And so what does that mean then if our limits on both sides don't match? Does it mean we don't have a limit? Does it mean we have some different kind of limit or something like that? So basically, if f, the function f, has a right hand limit at c, then we will write the limit as x goes to c plus. That means from the positive side, that little plus right there. So that's from the right, from the positive side. That's going to be this one up here. Let me do this in a different color here, like this. Let's do like green. That's going to be this limit over here. That's from the right. That's the plus one. Okay. And it's going to equal some value L. And the symbol x goes to c plus means we only consider values of x that are to the right of, so basically we're considering ones that are greater than c, or we could rewrite this as to the right of c. Okay, either way. Okay, then that's what I mean there. Everything to the right, so we're looking at all those green values over there. Similarly, if f has a left hand limit at limit m at c, then we write that. And this one, we'll make, what color here? Let's do that, I guess red, although I already had it in purple. But we'll do this, -1, and that's going to be this one right here. That's the left-handed limit. And we are looking for values that are less than c, or to the left of c, like that. Okay, and that's all those values. That's where we're looking. Okay, so now we can look at basically what are called one-sided limits. Okay, so let's take a look at example 1 here. Consider the function f of x equals the square root of 4 minus x squared. The domain here we want to look at is between -2 and 2, and we'll do that inclusive, so -2 to 2, inclusive. In fact, that is just the domain. We can't get outside of that. And so take a look here. If we look at the limit as x goes to 2 plus, so that's going to 2 from the positive side, all right? I'm sorry, goes to -2 from the positive side. Got to look at the little negative sign right there. And so it goes to from -2 from the positive side. What is that? So let's do that in red. And that's going to be as we approach from the positive side toward -2, right? We keep moving closer and closer and closer. So we maybe look here and then here and then here and then here. And what does our value get really close to? Where does it go to? It basically goes to 0. That's our y value right there. As we move further and further out, we get closer and closer to the x-axis, which is y equals 0. So that would be 0. If we take a look at the next one, we've got the limit as x goes to -2 from the negative side. From the negative side, that's from out here, but there's no values out here. Our function doesn't go below -2, so this is going to be does not exist because there are no values over there. None of the values exist, so there's no values to the left of -2. It's undefined to the left of -2. Okay? And then the last one here, let's take a look at, let's do, for this one, I'll use this purple here, the limit as x goes to -2 just in general. And what we're going to say here is it's 0. It's going to be 0 again. So normally this is the kind of limits we were doing before that we're now calling two-sided limits, where we had to look at both sides. And if we look at the left side over here, it doesn't exist. If we look at the right side, we go to 0. Well, why can we ignore the does not exist side? Well, we can ignore the does not exist part if and only if, all right, we're on the edge of the domain, which we are, because -2 is, again, right on the edge of the domain. If that is the case, we are allowed to ignore one of whichever side is outside the domain and only look at the side that's inside the domain. So in that case, this is 0. So basically, we are allowed to have a one-sided limit if, big if, the value is on the edge. The value is on the edge of the domain. Okay, so the last section, we didn't even talk about something like that, but now that we know about the one-sided limits, basically if we have a regular limit and it's on the edge of the domain, we can just do the one-sided limit of it, okay? So theorem 6, a function f of x has a limit as x approaches c if and only if it has a left-hand and right-hand limits. There are these one-sided limits are equal. Okay, so basically we have these limits, and we can say that our limit is going to be this if the left-handed limit equals out and the right-hand limit equals out. So our two-sided limit, this is two-sided, is going to be true if this one-sided and this one-sided are both equal to each other, if that makes sense. Okay, they both go to the same value, then our two-sided limit will have that same one. Exception being on the edge of the domain, where one can be does not exist if it's on the edge of the domain. All right, so let's take a look at this page right here, and let's look at some of these and determine these following limits based on the graph. Now, I'll do some of these, but then I'm going to leave the rest of them for you to try, but I'll put the answers in the notes, and you can ask me about any of them if you have any trouble. So let's see here. Maybe I'll do the first, 6 and leave the last ones for you. So let's take a look at the first one. Here's the limit as x goes to 0. So we're headed to 0 from the positive side. So we're going to 0 from that positive side. And so as I go towards 0 from the right, which is the positive direction, so I'm headed back towards 0, right? Essentially what we're doing is it's like we're walking towards 0 on x. This is 0 on x. And then what is happening to y as we do that? Well, as we move towards 0 on x, y is moving toward 1. So this is a 1. All right. The next one says the limit as x goes to 0 from the negative side of f of x. Well, if you look over here, there's nothing, there's no x values, there's no y values, there's no values. So we can't do that one. Does not exist. We can't even walk over there. It's outside of our domain. The next one, the limit as of f of x as x goes to 0, just in general. Here we can go ahead and say this is 1 because we had a limit of 1 as we went from the positive side, and then for the negative side we were on the edge of the domain, so they don't have to match in that one situation, which means this one can just be 1 for the regular limit. All right, let me do the next one for you too. Let's take a look at D. The limit as x goes to 1 from the positive side. So maybe we'll do this one in purple. As I go from the positive side, that's from the right, and I move toward the left, then I'm coming from the positive side. Then as I move here, I'm going right toward the value of 1, right? This is what y equals. It's 1 there. So this is going to be a 1. If I look at the limit as x goes to 1 from the negative side, then I have to come from the other side, from the negative side, which means I'm coming this direction, moving along the line from the left side. And as I do that, I keep getting closer and closer to 0, right? This is y equals 0 down here. So this one goes to 0. And now I have a situation where they don't match, and I'm not on the edge of the domain. So this is a does not exist. Okay, I don't have the same limit coming from both directions. Therefore, I don't have a two-sided limit. It does not exist, okay? So try these last 3 points. Take a look at them, see if you can figure them out. And then I'll write the answers in on the notes that you can then take a look at. All right? So here, if we know that the limit f of x exists, you find its value by calculating the limit f of x goes to x c plus. So give a think about that. And maybe I'll ask this or I'll write down a couple thoughts here on this in the notes. But you might be tempted to say yes as you think about this, like, oh yes, absolutely, immediately. But try thinking about something like that, where the limit does exist. We have a limit, we have a two-sided limit, but we can't find it by going from the negative side, right? So think about that and write yourself a little explanation there about, about what you think here, and I'll give a little, I'll write a little thing out for you to look at in the notes after you write yours out. Next, we're evaluating limits that involve algebraic values. So if we look here, we want the limit as x over x plus. And so if we take a look at that, that function is something we actually saw right back, where was it? Right back here, x over x plus. And so as x goes to 0, from the plus side, right, we can redraw that over here. Where was it? Our graph looks like this, where it's going to be 1, or actually that's a does not exist, so that's going to be a open circle and to the right, and then an open circle and to the left. So this is at -1, this is at 1. And so the limit as x goes from the positive direction, that means we're coming from here, is just going to equal 1. Okay? Try taking a look at this one, draw out the graph, and see what you can come up with for that one. And again, I'll put it in the notes for you to take a look at. Okay? Here we've got a crazy mess going on. So it is possible that a function does not have any kind of limit at a particular point of interest. And so if you look at this function, you can see that as you try to go towards 0, this thing is just going to go crazy and jump all around like crazy. And so we're not actually going to have it go to a single point and give us some sort of limit. It doesn't have a left-handed, so this y equals sine of 1 over x doesn't have a left-hand or right-hand limit as x approaches 0. And so what about this limit as x goes to 0 of x times the sine of 1 over x? What's going to happen to there? Well, the thing that multiplying by the x is that as x gets smaller in value, it's going to reduce it. So here we're bouncing back and forth with sine of 1 over x between -1 and 1. But if we start multiplying by x, what that's going to do is it's going to change the shape of our graph. Our graph is no longer going to look like that above. It's going to look kind of similar, where it's going to go something like this. And it's going to do like that, and then it's going to grow back up, okay, like that. And basically, as x gets small, it's going, and as x goes to 0, this x out in front, what it's going to do is force our function to be multiplied by basically 0, and it's going to squish down. which means we could actually take this and do like a pinching theorem on it, say everywhere this is, less than this parabola above it and this parabola below it, it's always in between those two, and therefore they go to 0, and we can say the limit as x goes to 0 of x, that's supposed to be 0, it looks like a 6, x times sine of 1 over x is just going to be 0. Okay? So we can use that pinching theorem on that one. All right, here is an important limit. This is one you most definitely want to know. And this is the idea that sine of theta over theta goes to 1. Essentially, this comes from the idea that sine of theta is approximately theta. This is in radians. In radians. All right, sine of theta is approximately theta for small theta. And then you can see in this graph that if you divide them by each other, they actually go to 1 because they get to be the same thing for small theta, but not, of course, at theta equals 0, because then at that point, sine of theta over theta is undefined. But they do get to be very close to each other. In fact, the sine of 0 is 0, so it kind of works there. But anyway, basically, this is an approximation that's used quite a bit. It's even used in physics. If any of you have ever taken physics and you've done what's called the pendulum, typically you remember it probably as a pendulum, but it's the simple pendulum. And basically, you had the idea of the swinging pendulum that would swing back and forth. But in order to solve that, we actually, if you go look back at any of your notes, if you did this in high school or anything like that, or in college or anything, you would have found that we actually used this approximation of sine of theta approximately equals theta, so that actually approached and acted like simple harmonic motion, and we could solve it. But make sure you understand then that this limit right here, if you're in radians, that the limit of sine of theta over theta is 1 as theta goes to 0. Okay, that's a very important one. Really can't stress enough. Make sure that you know it. So let's evaluate these limits here. And if we take a look at this one, we have the sine of the square root of 2 theta over the square root of 2 theta. Well, remember, sine of theta over theta, if we take the limit as theta goes to 0, is going to be 1. Well, if we say let square root of 2 theta equal something like, we'll just put x, I guess, then we can rewrite this as the limit as the sine of x over x, like that. And then this is going to be as what we want is an x over square root of 2 goes to 0 kind of a thing, because that's what theta would equal. And if we look at that, then this is as x over square root of 2 goes to 0. That's just x goes to 0, right? And so what we end up with there is we're basically just saying this is just sine of theta over theta as theta goes to 0. This is sine of x over x as x goes to 0. This is 1, okay? So that's the answer for that one, if you want to think of it that way. That's basically all we are getting out of that one. Okay, let's take a look at this next one. The limit of the sine of 2x over 5x. So if we think about this one, we can say that this is equal to, right? We can say, or here, I'll do it off the side, sine of 2x over 5x. What we can do is make this, is we can multiply both the top and bottom by 2. 2 over 2. All right? And when I do that, what I end up with is 2 times the sine of 2x over 2 times 5 times x. And if I just rearrange that slightly, I'll have 2 sine of 2x over 5 times 2x, right? I'm going to swap the 5 and the 2 because order of operation of multiplication isn't going to matter here. And then this means I have 2/5 times the sine of 2x over 2x. And that we can take the limit of, we just did something times it over there, as long as as long as these two numbers out in front here match, it's just going to end up being equal to 1. So taking a look here, we can rewrite this as equals limit as x goes to 0 of 2/5 times sine of 2x over 2x. And remember, the limit of a constant times a function is equal to just the constant times the limit of the function. So I can put this out front, 2/5 times the limit as x goes to 0 of sine of 2x over x. 2x, that was one of our logarithm rules. And I'm going to write that 5 a little better. And so this is just going to be, this part right here is just going to be equal to 1. So this is going to be 2/5 times, so our limit is just 1, which means our answer is just 2/5. Okay? And so that's pretty much the way you want to do those ones. If you see something like that, you want to make sure you get it to be that, just like that. All right, let's take a look at this one. Here, what we want to do is try this one here as t goes to 0. So here we've got tangent times secant, right? And so tangent, we can rewrite this one as limit as t goes to 0 of sine of t over cosine of t, that was our tangent, times secant is 1 over cosine 2t, just like that, and then we have the 3t times 1 over 3t. So we can basically just separate these out and take the limit of each one of these individually. So, right, because that was one of our limit rules, the limit of a times b is the limit of a times the limit of b. So if we take a look at this, we have sine of, sorry, we can rewrite this just a little more. So now that we expanded this out, this will be sine of t, and I'm going to take this t from right there and put it underneath it, sine of t, t. Then I'm going to do a 1 over cosine of t, and then I'm going to do 1 over cosine of 2t. All right, I'm just breaking these down into limits I can do, and then I just have this 1/3. All right, and so again, the limit of any one of these individually is the limit of each of them together, multiplied together. So sine of t over t, that limit is just going to be a 1. 1 over cosine. Well, what does cosine go to as t goes to 0? It goes to 1, so this is 1 over 1. And then cosine of 2t, it's also going to go to 1, so this is a 1. And then 1/3, the limit of a constant is just the constant. So that's what we have right there, which means ultimately, this is just 1/3. Okay? And then I wanted to do one more here with you just to kind of show you something. Maybe I'll put this up here just to give myself a little room. 1/3, like that. And yeah, I don't think, yeah, that just reduplicated that page. So anyway, let's take a look at this one here. Let's try to show that the limit as h goes to 0 of cosine of h minus 1 over h, we want to show that that equals 0. All right, so let's get to work on this. I'll do the rest of the solution here in blue. Limit as h goes to 0 of, and I'm going to take and do cosine of h minus 1 over h, and what I'm going to do is multiply it by its conjugate. So this is cosine of h plus 1 over cosine of h plus 1. Okay, and when I do that, what I can end up with here is limit as h goes to 0 of cosine squared of h, so cosine of h squared minus 1. Okay, that's just me multiplying this on the top times that. And then in the denominator, what you get is h times cosine h plus 1. Like that. Okay, and so then what I'm going to do equals is I'm going to pull out a -1 in the numerator. So this will be limit as h goes to 0. So I'm going to factor out a negative, and this will become 1 minus cosine squared h, like that, over h times cosine of h plus 1, just like that. And if you remember, 1 minus cosine squared is just sine squared. So this is going to be limit h goes to 0. 1 minus cosine squared is sine squared. So minus sine squared of h over our h times cosine of h plus 1, just like that. And after that, I can start splitting this up. And when I split this part, this will be limit as h goes to 0 of, and I'm going to put sine h over h. I can do that one, right? And then the other one, I'm going to put everything else. I'm going to put negative sine of h over, and I'm going to put the cosine of h plus 1. Just like that. Okay? And as I take this limit, this first limit here, right? If I take the limit as h goes to 0, the first one, that's just going to equal 1. The limit of the second one, well, as h goes to 0, sine goes to 0. So this goes to 0. And as h goes to 0, cosine goes to 1. And this goes to 1. So that goes to 1 plus 1, which is a 2. Okay? And so that's just 1 times 0 over 2, which is 1 times 0, which is just 0. Okay? So, like I said, the sine of theta over theta, and the limit of the sine of theta over theta as theta goes to 0 is very important. Make sure you remember it. Make sure you can use it. And that's pretty much it for this one. All right, thank you.